Okay, it's 7:30 and we're going to get started. Welcome to the February meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSC AS, and this is our agenda for this evening. We're going to start with the Mars 2020 mission, T-minus 6 days, with Dr. Raman Martinez with the Lunar Planetary Institute. Then Chris Wells will bring us a member's minute, yet more ESP Astro images. That's Eldorado Star Party. Then I will have a members minute M1 project part 2, and we'll wrap it up with David Haviland with Star Party News. If you have questions and comments during the meeting, you can submit them to the email address listed at the bottom of this slide, jscslive@gmail.com, or you can enter them as a YouTube comment if you have an account that will allow you to enter them into our YouTube channel in the comments area. Okay, so first up is our main speaker for this evening, Dr. Raman Martinez with the Lunar Planetary Institute. And I'd like to tell you a little bit about Dr. Martinez before we get started. Dr. Raman Martinez is a staff scientist at the Lunar Planetary Institute in Houston, Texas. He is a team member of the ongoing Mars Science Laboratory mission and co-principal investigator of the upcoming Mars 2020 mission, expected to touch down on February 18th, just next week. He is interested in Martian weather with focus on water and radiative environment and dust dynamics. With that, I'd like to turn it over to Dr. Raman Martinez.
Dr. Martinez, you have a go.
Okay, can you hear me?
Yes.
Okay, perfect. And you can see my screen, right? So ready to go?
Ready.
Okay, thank you very much. So hello, everyone. This is Raman Martinez from the Lunar and Planetary Institute. And it is my pleasure to be here with you today. Thank you very much for the invitation. So today I will be talking about the Mars 2020 mission, which, as you know, will be landing on Mars this upcoming Thursday at 3 p.m. Houston time. So feel free, or you are definitely invited to join NASA social media or even the web page, and we'll be broadcasting the landing live. So that should be hopefully a lot of fun. So I am co-principal investigator on this mission on the Mars 2020. That's why I am here today. And in particular, I led the scientific design of the requirements of one of the instruments on board the Perseverance rover. And I'll be talking about that later. And please, to make this talk more dynamic, feel free to interrupt me and feel free to ask me questions. And you don't need to wait until the end of the presentation, because otherwise you will be listening to me for 45 minutes and that might be too much. So please do not be shy and ask me as needed. Okay, so before getting into details, I wanted to introduce myself. I earned all my degrees in Spain, but you know, like in 2010, the crisis hit hard Europe. So I left. I went to Bergen in Norway. Then I went to Michigan to work at the University of Michigan in Ann Arbor for almost a decade. And then hopefully closing the circle and back to nice weather, I came to Houston in 2019 at the end of last year. Okay, so here I wanted to give you a taste of how easy or how hard it is to send a mission to Mars. So basically, like, I don't want you to count. So here I'm showing you what we call the Martian exploration family portrait. And again, I don't want you to count all the missions, but I can tell you that overall 49 missions have been sent to the red planet from 8 different countries. So you know, like the USSR sent the first mission to Mars back in the 60s. Then the US caught up shortly after that, and then after that, Russia, Japan, European Union, China, India, and recently the Emirates have joined the Martian community. And again, just to give you an idea of how hard it is to send a mission to Mars, around 50% of all these missions failed exactly, it's about like 47% of success. However, we have to say that we have learned a lot about our failures in the 60s, 70s, and 80s. And over the last 10 years, or indeed like over the last 2 decades, NASA has had a 90% of success. So obviously we will be very nervous when we land on Mars in a week from now, but we have to trust the NASA engineers. And again, you know, like it's been over a 90%, so that is definitely good. So let me mention some milestones of the Martian exploration. I'll go with the first flyby. The first picture of Mars was taken by the Mariner 4 in 1965. The NASA mission. Again, that was a flyby mission, and it was like pictures of the planet that basically let people know that Mars was not inhabited, because before that, you know, there were like many myths, particularly from the previous century, saying that, you know, like the channels of Mars and water and blah, blah, blah. Back at that time, we knew from telescopic observations that, you know, like Mars was not, you know, like a place to live, but definitely Mariner 4 in the 65 made that clear. Then years later, in 1971, Mariner 9, also from NASA, was the first orbiter on Mars. 2 years later, in 1973, the Mars 3 was the first lander on Mars. But the thing is that it only lasted like for 8 seconds. So I'm not sure if the problem was the antenna, the communication. But, you know, like that was, I mean, sort of failure. And then it was the Viking 1 and Viking 2 by NASA in 1975, the first landers that, you know, like worked for a long time from the surface of Mars. Indeed, these 2 landers were working for, if I will remember, 6 years. Not that I remember because I was alive. I mean, I wasn't alive back at that time. But even though this was the first lander on Mars, the data set that was recorded by the Viking landers is still very rich, and is definitely a reference. After the 70s, and I'm sure you guys know better than me, in the 80s and in the 90s, those decades were not particularly great for space exploration. You know, it was like a drought or sort of a desert in the exploration of Mars. But then starting in the late 90s, and definitely in this century, we are living a new golden age of Martian exploration, with a bunch of missions being sent every few years, and with a bunch of countries joining. As an example, in the last 10 days, you might have heard from the news that the Emirates, you know, like it's called Hope mission, was inserted into orbit on Mars. Then the Chinese mission Tianwen-1 is also into orbit on Mars, and in a few months it will deploy a lander to the surface of Mars. And then in 1 week from now, or next Thursday, we will be landing the Perseverance on Mars. Okay, so going to the next slide. And once again, guys, please don't be shy to ask me questions, really. So, okay, why do we send mission to Mars? I'm pretty sure that you know, but basically the defining question for Mars exploration, basically the driving science theme for NASA is there life on Mars? Basically, like, if we look for life on Mars, what is the first thing that we need to look for after? It's water. You know, like, we know that water is a necessary condition for life on Earth. So if we are looking for life on Mars, the first thing that we have to do is look for water. And indeed, previous NASA missions were designed under the follow the water science theme. Once we understood the water cycle and where the water reservoirs were on Mars, the next missions were sent to Mars under the theme Explore the Habitability. after after discoveries from all these missions were made, they paved the way to take the next steps towards finding evidence of life. And that is basically where we are now. And you can see here the green arrow. So the Mars 20 and 20 will be the first mission ever sent to Mars that will seek signs of ancient life. So I think this is like very important, because like previous landers and previous rovers and orbiters did not have the necessary instrumentation for this. So moving to the next slide here, if you are wondering, like, where on Mars do we send landers and rovers? So this is a slide, or this is a topic that I like explaining in talks. So what you are seeing here, guys, is the topographic map of Mars. So basically, you have the like northern latitudes above, southern latitudes at the bottom. So basically, like an Earth map. And what you can see here is the difference in altitude between the northern hemisphere, basically like the blue and green colors, and the southern hemisphere. So as you can see, the southern hemisphere is much higher. It's at a higher elevation than the northern hemisphere. And this is important when we send missions to the surface of Mars, because if you take a look here, you will see that most of the missions have been sent to equatorial and low latitudes. Now, if you are wondering why, this is the reason. Basically, in order to have a safe landing, we need a lot of atmosphere on top of us, so that the atmosphere can slow down the probe. Basically, we need friction from the Earth to slow down the rover as it, like traverses the atmosphere of Mars. And what happens in the southern hemisphere of Mars is that it is so elevated that you have a very thin atmosphere on top of you. It's like the pressure at the surface is much lower than in the northern hemisphere, because you are at a higher elevation, like here on Earth, if you go to a mountain. So this is why it's very challenging to land in the southern hemisphere of Mars. Also, some of these missions were solar powered. They were not powered with nuclear energy. So if we need energy from the sun, you rather go to equatorial latitudes, because then you have solar energy throughout the year. It's like on Earth, if let's say like Martians come to visit us and they rely on solar power, they rather go to Houston than to Minnesota, because otherwise they're gonna run out of battery. And that is literally what happened with us with the Phoenix mission that was sent to the northern pole of Mars. It only lasted for 3 months, because basically when the polar winter came and the sun, and we literally had no more sunlight, then that was the end of the mission. Obviously, that was planned, but, I think this is important to understand. Typically, we don't go to the most exciting and scientifically cool places. We go to the places that basically engineers feasibly allow us to go. I'm not saying that these are not cool places, but let's say that these are the coolest places among those that we can reliably visit.
Okay, we have a question that's come in.
Always, yeah, sure.
To what extent might one nation's Mars mission need to help another nation's if there was trouble? And are there space maritime laws?
Okay, so regarding the laws, I think that this is something that is under development. I honestly don't know much about it, but I certainly know that the US, Canada, the European Union, Russia, China have talked basically about creating a common law on Mars. So that is under discussion, and this is going to be very important in the next decades, I'm pretty sure. And then, sorry, the first question was about different countries helping each other?
Yes. Say one nation's mission got in trouble,
Okay. Yeah.
What could another nation do to help?
That's an excellent question. Okay, so that's a very good question, because basically, if we send a lander to the surface of Mars, the way we get the data back on Earth is because first we transmit the data from the rover to an orbiter on Mars. Then from the orbiter on Mars to the Deep Space Network on Earth. So basically, for instance, now the Mars Science Laboratory, the Curiosity rover, which is a NASA mission, is typically transmitting the data to the European orbiter. So obviously, with the European Space Agency, we have a great relation, and we definitely work together. There are other missions that are a little bit more opaque, but like it's mandatory. Basically, like at some point we will have to collaborate, because as of now there used to be only 2 orbiters. Now the Chinese and the Emirates are there. So we need collaboration to transmit data. Again, like with the Emirates and the Emirate mission is basically like, a lot of the instruments are from the US, from LASP, from a department in Boulder, Colorado. So there is a great, cooperation between Emirates, the US, between Europe and the US. Let's see what happens with other missions. But yeah, we will need collaboration.
Okay. Another question. Do you know what ground stations are used to receive the data from Mars, like Goldstone or White Sands, etc.?
So there are 3 that I know, and I'm gonna tell. So one in California, one in Spain, and one in Australia. So those are the 3 locations with large communications antennas to receive the signals. I don't know exactly where in California, then Madrid in Spain, and somewhere in Australia, and I don't know the place either. Okay, so more questions here?
No, go ahead.
Okay, awesome. Okay, so now that we have some Martian context, let's focus on the Mars 20 and 20 mission. Again, it's coming, it will be touching down in 6 days, and please feel free to follow live on the NASA webpage and social media. So, as I said before, past missions have followed the water and explored the habitability of Mars. So now it is our time to take the next step and seek evidence of ancient life. Have in mind, please, that I am saying ancient life. So we are not hoping, or we are not expecting to find, little green men. We're talking about ancient life, okay? And not even about current microbes, because we are exploring the surface, and it is extremely unlikely that current life can evolve at the surface of Mars, because basically it is bombarded by high energy particles from the sun that are not deflected on Mars, because Mars doesn't have a magnetic field. So basically, here on Earth, we live because we are not frightened by these particles from the sun that reach the surface of Mars. So, okay. So, as you can see on the right, Mars today, at least on its surface, does not have the characteristics of a habitable environment. It is super cold, it is very dry, it suffers intense bombardment by energetic radiation from the sun that, once again, is not deflected because it doesn't have a magnetic field. And also the ozone is there's little ozone on Mars. So it's not only UV radiation, but even higher energetic radiation. But it wasn't always like this, and that's what we are showing artistically on the left figure. In the past, we believe that Mars had liquid water running on the surface, and the conditions were warmer and wetter because the atmosphere was denser. So we believe that Mars had all the basic building blocks of life, which still should exist on the surface today. And these building blocks of life is what we are trying to find. Okay, so what I'm showing here is the landing site of the Mars 2020 mission, and this is called JSC crater. And we believe that this is the home of an ancient delta. And sorry for the typo to an ancient data. This happens. I hate when I see this, but yeah, again, this happens. So why are we going to what we believe that was a delta of a river? Well, because, JSC has rocks and minerals that can only form in water. And, some of these rocks that formed in water are commonly associated with life on Earth. So this is a great place to look for signs of habitability and of past life itself. As an example here on the next slide, this is an Earth analog to JSC, and this is the delta of a river in Alaska. And again, this is a silly comparison, but it works. Imagine that in a billion of years, Martians are coming to Earth to seek for evidence of past life. They rather go to a place like this, to a delta like this, than to the Sahara Desert in Morocco or Algeria. So again, this is why we are going to JSC crater.
Okay, we have a question here.
Of course.
If the water had existed like you're describing in the delta environment, what is the leading theory as to where the water went?
Okay, so basically what we believe is that the dense atmosphere that hosted liquid water on the surface started to be lost. So basically, the gas components making up the old Martian atmosphere started to be lost out to space because of intense bombardment from the sun. And basically, as the atmosphere was shrinking, liquid water started to evaporate because if you have a thinner atmosphere, you don't have greenhouse effect. So basically, the temperature at the surface is colder. So as you lose the atmosphere, temperatures drop. And as temperatures drop, liquid water changes to water ice. And in addition to that, water vapor in the atmosphere, is stripped out of the atmosphere. So that's basically the leading theory. So we moved from a wet, warm Mars to a cold, dry Mars, which is what we have today. So hopefully that answered the question. More questions related to that?
Not to that, but we have another one that came in. How do you determine altitude on Mars since there's no sea level?
We take a convention. That's a convention that we take basically. And we define the reference as 6.1 millibars. And that is totally a convention that we have made up. So basically, we normalize everything to a pressure of 6.1 millibars, whereas on Earth, we normalize to the pressure on sea level. So that is a convention that works for us scientists and helps us normalize everything so that we can compare apples to apples. But it's a convention. Okay, more questions?
Not at this time.
Okay, so once again, we know that Mars once had what life needs. We are not saying that it had life. We are saying that it had, the building blocks of life. So how is this mission trying to look for that evidence? So in this slide, so basically to understand the possibilities for life on Mars, this mission will try to fulfill 4 very ambitious goals. So 3 of these goals are about the search for ancient microbial life. That is objective A, B, and C, geology, astrobiology, and sample caching. And then the last objective is about preparing for human exploration of Mars that hopefully will occur in the next decade, couple of decades. We are not really sure, but I like saying that it's very likely that the first man or woman setting foot on Mars is already alive. So hopefully, we will be able to see that. Let's see. But okay, let me talk a little bit about these 4 goals, which again are related to the main overall goal, which is searching for searching for evidence of past life. Okay, so hopefully this is not boring, but this is how we will be working, so it's interesting nonetheless. So goal 1 is to carry out an integrated set of context, contact, and spatially coordinated measurements to characterize the geology of the landing site. So basically the way this works, you can see on the left that the landing site is first studied from orbit, and then basically we have different instruments that will probe the immediate neighborhood, the terrain, its various rock formations, and basically down to the microscopic level. So in other words, before we go straight to look for evidence of past life, we need to recognize the environment. We need to take a look to the left, to the right, to the bottom, and we need to basically, using our eyes, using our camera, we have to understand the context. We need to understand where we are at to tell the rover, oh, let's move to those rocks, or let's move to the other. So we need this kind of context. I myself am not a geologist, I'm a physicist, but I have to share with you that 90% of the people involved in missions are geologists. So basically they are, sort of the, they are an important part of the Martian exploration, the geologists. So moving to the next goal, astrobiology. The main astrobiological goal will be to find and characterize ancient habitable environments. And for this, we will identify rocks with the highest chance of preserving signs of ancient Martian life, if it were present. And then we will go to those rocks with the rover, and within those environments, we will seek the signs of life. So once again, goal 1, geology, we take a look around. Goal 2, we identify rocks. We go to the rover for those rocks, and basically we probe those rocks. Goal 3 of this mission, and this is huge. Well, goal 2 is also huge because, again, an astrobiological goal has never, this is unprecedented, the fact that we're looking for life. Goal 3 is also unprecedented. So there's a lot of unprecedented stuff with this mission, and that is obviously great. So the goal 3 is to collect samples. So we want to place rigorously documented and selected samples in a returnable sample cache for possible future return to Earth. And here, guys, you have to understand one thing. The instruments that we send to Mars are limited by their mass and energy consumption. So even though technologically speaking, the instruments that we send to Mars are great, gorgeous, and awesome, still the most powerful laboratories and instrumentation is here on Earth, because obviously we don't have the mass, energy, and money limitations. So this is why we want to return samples to Earth, so that we can make sure to better, constrain the rocks and to make more accurate, discoveries. Okay, I'll be talking more about how we will collect samples and how we will be returning those to Earth. and when will that happen, which is everything a little bit open, but I'll get back to that later. So
got a question
sure.
that came in. Back on that image of the Jezero Delta photo, is that color enhanced?
Yes. It is color enhanced to show the different minerals. So basically, like using an orbital spectrometer, like we identified different minerals based on their spectral signature. So it is definitely color enhanced. Yeah. It's convenient, it's convenient and pretty, I guess. Okay, so for goal, the last goal is to prepare for human exploration. And basically, this is a threefold objective. The first thing that we want to do is to demonstrate technology for future human exploration. So basically, for the first time, we want to react atmospheric CO2 to make oxygen. So again, this will be a technology demonstration. And as you know, the atmosphere of Mars is 96% CO2. And definitely whenever we go to Mars, we will want to breathe oxygen. So we have to figure out how to make a breathable environment. So we will be, we have an instrument that will prove, that this conversion can be made from CO2 to oxygen. Second, and also very important, we want to characterize the atmospheric dust size and shape, because we want to understand its effects on the operation of surface systems and on human health. As you know, guys, like it's not good to breathe or inhale aerosols that are, let's say shorter than a few microns. And that is literally the size of a Martian airborne dust. It's typically like about 1-2 microns. So we need to understand, we need to be prepared in terms of health risks for astronauts. And also, we don't want this little dust to infiltrate into, the machinery or instrumentation that we will be sending. We don't want this dust to screw up the, the proper functioning of this instrument. So we need to understand this interaction. And finally, and this is also very important, we need to understand the dust size and shape, because in order to forecast the weather on Mars, we need to understand how the dust interacts with the solar radiation. And this interaction between the sun and the dust depends a lot on the shape and size of airborne dust. And obviously, whenever we go to Mars, we want to be able to predict the weather, because we don't want to be caught in the middle of a local, regional, or global dust storm. So at least we want, we will want some days in advance, definitely. Okay, so once I presented the 4 goals, now I will introduce you to the payload of the Mars 2020 mission. So basically, how are we going to achieve these 4 goals? By utilizing these 7 instruments. So out of these 7 instruments, 5 were built in the US, and then we have 2 foreign contributions. The weather station, which is MEDA, this was built in Spain, and then we also have RIMFAX, which is a contribution from Norway. And if you are wondering why NASA has instruments contributed from other countries, my opinion is that the answer is twofold. On one side, it is good to alleviate basically the budget from NASA missions, because basically Spain and Norway paid for the development of these instruments. So this is money that NASA saves. And also, it's definitely good to enhance international cooperation. So it is very likely that one country alone is not going to be able to, significantly advance in the human exploration of Mars. So we need to coordinate with the Europeans. We need to coordinate with the, we need to coordinate with as many people as possible, as many countries as possible. So that is the reason why we have 2 foreign contributions here. Okay, so now I will go one by one, explaining the 7 instruments that we have on board. So the first one is Mastcam-Z, and this will be our eyes on the Perseverance rover. So Mastcam-Z is called like that because it's a camera that is sitting on the mast of the rover, and Z stands for zoom, because the camera that we have on board the Curiosity rover doesn't have the capability to zoom in. So that's the reason for the name. And this Mastcam-Z has cameras that can zoom in, focus, and take 3D pictures and videos at high speed to allow detailed examination of distant objects. So basically, this is how we will be able to identify rocks of interest. If you want to know, this is not gossiping, this is open information, but just to give you an idea, the color quality of this camera is similar to that of a consumer digital camera, so 2 megapixels. The image size is 1600 by 1200 pixels, and the resolution is about 150 microns. Again, I'm pretty sure that there are better cameras on Earth, but remember that this is a matter of energy, mass, and funding. So, we don't always get what we want, but what we can. Yeah. Okay, moving to the next instrument, SuperCam. This is basically the one that draws the most attention because it shoots a laser, and nothing beats shooting a laser, I guess. But basically, the SuperCam will examine rocks and soils with a camera, a laser, and spectrometers to seek organic compounds that could be related to past life on Mars. So basically, ChemCam can identify the chemical and mineral makeup of targets as small as like a piece of hair that are up to 20 feet far from the rover. And so this will definitely be an important instrument to seek evidence of past life. So moving to the next slide, here we have PIXL, and this is a great name in my opinion. So, okay, PIXL stands for the Planetary Instrument for X-ray Lithochemistry. And it has a tool called an X-ray fluorescence spectrometer. And this fluorescent spectrometer will identify chemical elements at a very tiny scale. PIXL also has a camera that takes super close-up pictures of rocks and soil textures. And basically, it can identify features as small as a grain of salt. And PIXL and SuperCam will be instrumental to seek for evidence of past life. Moving to the next slide, this is also a very cool name. So SHERLOC stands for Scanning Habitable Environments with Raman Luminescence for Organics and Chemicals. And this will be the first UV Raman spectrometer to fly to the surface of Mars. SHERLOC will be mounted on the rover's robotic arm, and it will use spectrometers, a laser, and a camera to search for organics and minerals that have been altered by watery environments and maybe signs of past microbial life. So SHERLOC and PIXL indeed will be key to seek for this evidence of past microbial life. Also, interestingly, SHERLOC will be the first instrument to carry a Mars meteorite on a round trip home. So, like we got a Martian meteorite fell on Earth, and as a calibration target, SHERLOC will be bringing this piece of meteorite back to Mars. I don't know more details, but I think that this is like a cool aspect. Okay, so moving to the next one, Watson. So indeed, Watson is part of SHERLOC, and Watson is a color camera for taking close-up images of rock grains and surface textures. So you know, like the point here is that SHERLOC and Watson will investigate the crime scene, you know, and they will use UV fluorescence light as you know, like FBI people do, and you know, that's a little bit the context explaining why this was called SHERLOC, which again I think it's genius. Okay, moving. Well, this is not moving to the next instrument, but basically here, Mars 2020 will look for biosignatures that are. But biosignatures can be very diverse, and this can be objects, substances, or patterns that can only be created by life-based processes. So, you know, for example, this could be patterns in the rock, or this could be isotopes of chemicals that only life could have left behind. And this is what we call a fingerprint of life. And again, this is what SHERLOC and PIXL and SuperCam will be looking for. So moving to the next one, and let's go with the Norwegian instrument. So RIMFAX stands for the Radar Imager for Mars Subsurface Experiment. And this will be the first in situ radar to see geologic features under the surface. So what this instrument will be doing is to probe the ground under the rover. And basically, depending on whether you have water ice, liquid water, rocks, sand, or loose material, the sonogram that you will be taking back will be distinct, you know. So basically, based on the sonogram that RIMFAX will be measuring, we should be able to figure out whether, you know, what we have below the rover is water ice or very dense rocks or very fine grained material like dust. As you might know, we have a Martian radar, but that's working from the orbit. So this is gonna be the first radar, you know, like working in situ. Okay, next slide. And here we have the weather station. And indeed, this is the instrument that I am co-principal investigator of. So MEDA stands for the Mars Environmental Dynamics Analyzer. And this will be the weather station on board the Perseverance. As a typical weather station on Earth, it will measure wind speed and direction, pressure, relative humidity, air temperature, ground temperature, and radiation in the solar and infrared wavelengths. So MEDA has two objectives. The first is to assess the effect of airborne dust on surface systems and on human health by characterizing the size and morphology of the dust. And the second objective of the meteorological station is to improve the predictability of forecasting models by measuring surface weather conditions around the clock. So basically, we will test our forecasting models against these weather measurements to improve their predictability. And I could talk for weeks about this instrument, but it is not the right time. But this is basically the instrument I have been working for the last 6 years of my life. So anyway, moving to the next slide. This is also a very cool instrument. So this is MOXIE, which stands for Mars Oxygen In Situ Resource Utilization Experiment. And this MOXIE will demonstrate a way that future explorers might produce oxygen from the Martian atmosphere for propellant and for breathing. So we not only want oxygen to survive, but we also need it for propellant. MOXIE will simply is not the right word. MOXIE will demonstrate that this technique is feasible on Mars. And if it is correct, then basically the next instruments that we will send to Mars will be able to create in a massive scale oxygen, once again, for breathing and for propellant. And yeah, once again, like natural oxygen on Mars is only 0.13% compared to 21% on Earth. So we definitely want to create oxygen. Okay, it's 8:15, so I have some more minutes. So for the first time, the Perseverance will collect 35 samples of Martian rock and regolith. And each of these 35 samples will be about 15 grams each. And they will be drilled into sterile sample tubes and deposited on the planet's surface. Then these tubes will be returned to Earth by follow-on missions, likely in the next decade, and subsequently analyzed in the most advanced labs here on Earth. For you to have an idea, basically these tubes have the size of a cigarette, and we have like 40 of these. And again, like we will be collecting samples, digging these samples into the surface, making sure to know where they were deposited, and then in the future will be brought back to Earth. So this is just an illustration of how the sampling and caching strategy will work. Honestly, we don't know whether we will deposit all the tubes in one place or whether we will be depositing them along the traverse. As you can imagine, this is risky because if you decide to keep them all and then at some point deposit them, what if something goes wrong and we lose communication? Then, like they wouldn't have been deposited on the ground. But at the same time, if you want to retrieve them in the future, it is easier to have them all in the same place so that, like the retriever rover in the future don't go finding places. So anyway, this is something under discussion. Moving to the next slide, this is a notional 3-mission Mars sample return campaign. This sounds a little bit too much, but it's not, I guess. So we are here. We will be collecting samples. Then a coordinated campaign between the European Space Agency and NASA will send a lander retriever that basically collects the sample with a rocket that will be able to go to the Martian orbit, and then another different mission will send a orbiter to Mars to catch the samples in the rocket and bring them back to Earth. And this is supposed to occur next decade. And finally, I want to talk about the helicopter. The helicopter named Ingenuity is a flight test. It doesn't have a scientific objective. It's basically like a technology demonstrator. So this will be, if it works, it will be the first helicopter to fly on Mars. And this is hard, guys, because Mars has a very thin atmosphere. So we don't have drag from the air, which makes on Earth, like helicopters fly in a simple way. On Mars, we don't have air, we don't have dense, we do have air, of course, but it is not dense. And this is why it is complicated, like to fly things on Mars. But if this works, this is gonna be amazing because it will open the doors for future drone mapping of Mars, like in future human exploration, if we want to visit a cave or if we want to recognize whatever is behind a mountain, we will send our helicopter and take a look. So we need to demonstrate this technology. And now it's already, so yeah, it's Okay, so this is going to be the end of the presentation. I'm going to go fast here, but this is just the sequence starting from when we launched the rocket last July. Now we're going to Mars, getting close to Mars, and this is just the landing strategy. First, we will have a parachute that will be deployed. After that, we have like thrusters that will slow down the rover. We will use AI to recognize the terrain and make last minute moves to the right, to the left, to, we don't want to land on a rocky terrain. And this is a little bit, we have a shield, obviously, because temperatures will be warm. Then we will have the parachute. After that, we will have the thrusters slowing down the probe. Then what we call the sky crane with these rods here, and hopefully a smooth landing. And sorry, I'm going fast here, but this is how it works: the EDL phase, entry, descent, and landing phase. And once again, we will be transmitting the data by first from the rover to an orbiter on Mars, then from the orbiters to the Deep Space Network. And we have large antennas in California, Spain, and Australia. This is just it takes 30 minutes to communicate with Mars. That's basically whenever we tell the rover to do something, it takes 30 minutes. And finally, remember that we don't have a solar panel on this mission. We rely on nuclear energy, which is definitely better because global dust storms will not ruin our operations. But at the same time, understand, guys, that this is much more expensive. So at some point, we will have to rely on solar energy. And the nominal strategy, the nominal duration of the mission is 1 year. And although, for instance, the Curiosity rover, this is our 9th year of operation, so we hope to last definitely more than 1 year. And this is it. This is a summary of the objectives, and this is what we try to achieve with this mission. So hopefully I was didactic, because that was my intention, and you might have learned something about missions to Mars and Mars 2020. Thank you very much, guys, for listening to me for such a long time.
We have several questions for you that have come in. I didn't have a chance to break in. Could you clarify why you think Mars was considered habitable when it doesn't have much of a magnetic field or oxygen atmosphere and density?
Oh, it was considered habitable because at that time it had the conditions for life to show up. So in the past we believed that Mars had indeed the conditions for life. And what we believe is that now those conditions are not met anymore in the surface, but we believe that the building blocks of ancient life still exist at the surface. And that is exactly what we are looking for.
Okay. What are your thoughts on the likelihood that microbial life on Mars, if found, came from Earth via meteorites?
Via meteorites. That is hard, obviously, because microbes will be fried as they enter the Earth atmosphere. So, that's basically like a natural way to sterilize stuff coming from the universe. But that is a very good question, because planetary protection is a big thing now in NASA. So basically, we have to make sure that everything that we send to Mars has been sterilized. That basically, we have to make sure that we cannot carry Earth microbes to Mars. And conversely, we have to make sure that in the sample returns, we don't bring microbes from Mars back to Earth, if at all, because basically we don't want to play God with Mars, and we don't want to bring a virus from the universe. So planetary protection has very strict protocols, and we have to follow those, and all the instrumentation has definitely been sterilized so that this does not happen, to prevent backward and forward contamination.
Okay, how deep can RIMFAX penetrate below the surface?
It's gonna be 1 meter, a few meters, but I think it will be around 1 meter, if I will remember. I'm talking from the top of my head, but I think it's gonna be like 1 meter, around that.
Is there a radiation detector on Perseverance, like cosmic rays, gamma radiation, etc.?
Not this time, because we have one on board the Curiosity rover, which is the RAD instrument, RAD. So we have already accurately measured the doses of this high energetic and harmful radiation. So we don't have an instrument measuring the most harmful solar radiation, but we do have instruments measuring solar radiation from the UV to the near infrared.
Does Perseverance have the power to operate RIMFAX continuously, or because of power usage, do the instruments need to take turns being used?
Yeah, I mean, I don't think that we need to operate RIMFAX continuously, because have in mind that we're not moving all the time. Like even with the Curiosity rover, it is very likely that we go to a place, we move 10 meters, and then we spend 3 sols at the same location. So basically, it's enough to take, to probe the surface once until we move to the next place, so it won't be necessary to run RIMFAX around the clock. And that's a very good question, because even though we have nuclear energy, we are energy limited. So it's not that we can measure whatever we want at any time. We basically have to, in simple words, we have to ask permission, and we have to make a very good scientific case if we want to measure differently from the nominal measuring strategy that has already been established. So basically, if we want to go beyond our share of energy, we have to make a good and compelling scientific case. But again, with RIMFAX, it's not strictly necessary to measure around the clock, because we will be on top of the same location for days, likely.
Okay, we did have another question that came about the plans for the Mars helicopter, but you answered that, and the commenter sent back that never mind, you covered it.
Okay. Did I answer a question about
No, it was, she wanted to know about it in general, and you covered the material, so she said never mind.
Yeah, no, like to say a little bit more about the helicopter. Once we land safely on Mars, I think that it will take like a couple of months for the helicopter to be deployed and to be flown, because basically the helicopter is in the belly of the rover. So basically we have to make sure that we take it out from the belly, and after that we have to make sure the helicopter is solar powered. So basically we have to expose it to the sun to charge its batteries. And then, all these little steps take time. And I think that it will be after a couple of months that the helicopter will fly for the first time.
All right, we got another one here with the his past history of water and minerals. Would you expect to find fossils of bacteria on Mars?
That would be awesome, but hard in the surface. I don't think that is likely. But not because there were not fossils on Mars, but because if they were, they might be more easily preserved in the subsurface, because the subsurface is not exposed to high energy particles from the sun. So a fossil basically is that would be great. I'm not saying that right at the surface we cannot find evidence of ancient life, because that is exactly the goal of this mission. We can, But I think that the signs of past life at the surface might be more subtle than a fossil, because the conditions at the surface are very aggressive, because of this radiation, whereas in the subsurface, the preservation might be more easily achieved. The thing is that first we have to start with instrumentation that can probe the surface, and after that we will have time to develop technology that will dig into the subsurface. And as you know from the InSight mission, that is not simple. The InSight mission is the lander that tried to drill the first meter of the Martian surface, the mole, and it couldn't, because basically we thought that the surface of Mars would be a little bit different from what we found, and that this is where the mole couldn't work. So what I'm saying, like, we start with the surface and then we will go to the subsurface. That will come later. The subsurface is more likely to have signs of past life, or at least better preserved. But, so again, would be amazing to find a fossil, but I find it unlikely.
There was just a comment made about the sample tubes from another individual that was talking about that they worked with those directly, and each tube was $70,000 to create, and they went through 100 different samples to find the best way to do that.
Yeah, I wasn't part of, I'm part of a different instrument, but I'm sure that was like a very challenging process, because, you have to sterilize the tubes. They have to be of a particular material, and it's like very challenging technologically speaking, definitely.
Okay, looks like we've got one last question here. Are experiments allowed by regular folks using data already collected by NASA missions? For example, I'd like to analyze communication frequency changes as spacecrafts move toward and away from Mars.
Oh, so sorry, what was the question? Like, how can he or she retrieve those data?
If it's asking, are experiments allowed by regular folks using data already collected by NASA missions? So basically, can regular people get the data?
Yeah, of course. Oh yeah, no, and that is like mandatory by NASA. So basically, like, all the data measured by any NASA mission are available in what we call the NASA Planetary Data System, PDS, Planetary Data System. And basically, we have the duty to make those data available to the entire world. And those are open access. And I'm not talking about the raw data from where only, like people working inside can obtain science data. No, I'm talking that we have to post publicly the science data. So basically, anyone, you guys can go to the PDS, NASA PDS, and download the data of temperature, humidity, mineral composition, or whatever of any NASA mission. The similar thing goes to European missions. As far as I know, I've tried to go to, like Chinese web pages to retrieve data and couldn't make it. So hopefully in the future, their data will also be shared. But for the time being, like NASA and ESA missions, that they have to, because basically we want everyone on board. We need as many people as possible. So yeah, all available.
All right, thank you. I'm going to give you a break, and we'll go back to Doug.
Thank you very much.
Doug, you have a go.
Okay, thank you very much for that very interesting talk, and very timely, since this mission will be getting to Mars next week. So thank you very much for that talk. Next up, We have a members minute with Chris Wells, yet more Eldorado Star Party Astro images.
Chris, you have a go.
Okay, good evening. I've got more Eldorado Star Party images. These were a set of about 30, I think, images that I took in October of last year. Probably my most successful trip to West Texas. And I took a number of different rigs there and strung together a number of photos. The latest that I've processed, just in time for Valentine's Day, is the Heart Nebula that's in Cassiopeia. And I took the picture of the Heart Nebula using a number of different setups. The first one in a top right-hand corner was a Sky Guider Pro mount. That's actually Trevor's mount with my camera, and that was a wide field image. I also took sort of a medium field image using a small Takahashi telescope, which I'm calling a hitchhiker because it was hitchhiking a ride aboard a C11 telescope, which had a hyperstar setup and a nice cooled Astro camera on it. So you can think of this as I've got a wide field image, I've got a medium field, and I've got a zoomed in image as well of the center of the Heart Nebula. So this is the hitchhiker or the small Takahashi view of the Heart Nebula, and it really does look like a heart, doesn't it? It's it was about 25 different images that I took, each being 5-minute duration. The field of view is about 4.4 by 2.9 degrees, and with a bit of processing, you could really push the colors and really stretch the histogram on this picture to bring out that very characteristic heart shape. So it's very, very well named. So, So where is the Heart Nebula? Well, this is the wide field image. This is just using a DSLR camera. It's actually placed really on the boundary or between Cassiopeia, which is on the bottom right here, and Perseus, that's over here. One of the recognizable objects close by is the double cluster. See the double cluster there? And the Heart Nebula is right there. And a wider field image would actually show you the Sol Nebula around that area. And I'll have to go back one day and take an image of that area because I don't have a good close-up of that. But I do have a good close-up of the Heart Nebula here. And this is just taking with the Sky Guider Pro mount. It was 24 images just at 2 minutes each. And that's total field of view of 22 degrees by 15 degrees. So that's really, really wide. And lastly, this is the image I just finished processing a few days ago. This is what the Heart Nebula looks like right at the heart. So if you like, this is the heart of the Heart Nebula. Absolutely love the detail at the in the center there. All that nebulosity, all those patterns, and the dark nebula in different places as well, and the different colors. Absolutely love that picture. And that's what the heart of the Heart Nebula looks like. And that's all from me. So have a good Valentine's Day on Sunday.
Back to you, Doug.
All right, Chris, thank you very much for that. And I'm really enjoying seeing your images from the Eldorado Star Party since I was there with you and now getting to see the results of all this. So thanks for sharing those and continue to do that. We hope you'll show us the rest of them when you get them processed. Okay, next up is a member's minute of mine, M1 project part 2. So last month I showed you my M1 project part 1. And what I've been doing this month, or this winter, is I've been concentrating taking images on M1, the Crab Nebula. Instead of taking a lot of different images like I normally do, I've actually been concentrating on one and looking at it in different ways. So for all the images that I've taken of the Crab Nebula, I've used this setup. It's an AT8RC Ritchie Cretion 8-inch f8 telescope with a field flattener And then I have taken the supernova remnant in narrowband, which is sulfur, hydrogen, oxygen. I've also done LRGB imaging, luminance, red, green, and blue. And then today I'm going to show you, in addition, my near-infrared image of the Crab Nebula. They're all taken with an Sony ICX 285 based CCD camera. And then I use a guider MT9M034 CMOS based guide camera with an off-axis guider. And I run the whole thing remotely with a Raspberry Pi so I can sit in my warm house and not have to freeze to death out in the backyard with the telescope. So, okay, so last month I showed you this image. This is my narrowband image of the Crab Nebula, and it goes downhill from here. So this is probably the best one, but I showed you this one last month. I also have taken the Crab Nebula in LRGB. So this is luminous, red, green, and blue. And then the new image I'm going to show you this month is a near-infrared image of the crab. So near-infrared, what is near-infrared? Infrared is anything that's beyond visible. So visible light is 400 nanometers to 700 nanometers. Anything wavelength longer than 700 nanometers is considered infrared. And near-infrared means it's near the visible light. So anything close to 700 nanometers, that's near-infrared, close to visible light range. So these particular near-infrared filters, there's 4 of them. One is called a luminance filter because it covers the whole range from 700 nanometers out to where the CCD cuts off, which is about 1100 nanometers. That's the longest wavelength that silicon detector will actually produce electrons and hole pairs when a photon hits it. The red is beyond 888 nanometers. Green is a filter that's for 800 to 900 nanometers, and the blue is 700 to 800 nanometers. So you look at this image, and it's probably not as good as the other ones, I would have to admit, but it is interesting to see what it looks like in near-infrared. There are some advantages of near-infrared. One thing is that you'll find out that in near-infrared, there's very little or no light pollution. So if you live in an area that has a lot of light pollution, doing near-infrared astrophotography actually is a big help. You can actually do things that you couldn't do in visible light range. Now, one of the downsides of doing near-infrared imaging, you kind of notice that a lot of these stars in this image look a little fat. And what's going on here is not that they're out of focus. What happens is, as your wavelength gets longer, we actually have an issue with absorption depth in the silicon. And what that means is the longer your wavelength of your light is, the farther the photon can go into your silicon before it gets absorbed. And what the result of that is sometimes a photon that actually starts out in 1 pixel, if it can be absorbed in an adjacent pixel. So it makes it so that the focus or the end resulting MTF, the modulation transfer function of the image, is not as great because the incoming photons actually may not wind up in the pixel you want, but they may absorb lower in the silicon and wind up into an adjacent pixel. And for my images, the thing I see the most difference is it's just overall the stars are a little fatter. But it does look slightly a little different. And then here's a comparison of the 3 different versions of the Crab Nebula that I've taken this winter. The LRGB image in the upper left-hand corner, which is what we would normally see, color image. The upper right hand is a narrowband, which of course is my favorite because it shows the most detail and most interesting, I think. And then the bottom one is near-infrared, which is a new one I've added for this month. And I think that's probably going to be about it on M1 for me this winter, but I thought it'd be fun to image it in different ways and take a look at it with different wavelengths of light using the same camera and same telescope setup. And yes.
You got a question here. Are you able to measure the redshift on the stars?
Am I able to measure the redshift on stars? Yes, but not. Okay, that's a different topic, but yes, actually, in one of my other presentations, I showed you that I've messed around with spectroscopy. And in fact, one of our speakers that we had a number of months ago, Tom Fields, was a fellow who sells RSpec, actually wrote the RSpec software and sells the diffraction gratings and software that allows you to look at the spectrums of stars and actually look at redshifts and actually characterize what different types of stars they are on the HR diagram. So I hope that's what you're asking. But yeah, it is possible to do that. I did not do that in these images here, but using RSpec and others like a slit spectroscope, spectrograph, sorry. Yeah, you can measure the spectrums of stars and look at redshifts yourself, which is kind of cool to do.
And also, they commented that you're cheating by staying inside.
I am cheating by staying inside, but let me tell you guys something. I spent a lot of time out in the backyard, and it was cold, and sometimes it rains on your equipment, and things happen and all that stuff. But since recently, actually, a guy named Brad Thomas, I don't know if Brad's with us tonight, but Brad came to our astronomy club and started talking to us about using Raspberry Pis and other small computers for running your telescope. And myself and Trevor and Chris and some other folks in the club, kind of a light turned on our head, and we thought, oh my goodness. And instead of being out in the backyard with my expensive laptop in the freezing cold, now I got a $35 Raspberry Pi running the whole thing. And yeah, I sit inside in the nice warm house and do the whole thing remotely. So there you go. All right, that's it. And next up.
Hey, hold on. You got one more question.
Oh, one more. Okay.
How do you expect seeing to be with the upcoming cold front?
I don't know, but I'll tell you something. I'm looking forward to it because I'll tell you what, the colder the equipment is, the better it works. So cold is good. In fact, this image here, this narrowband image, I did some of this on nights that are a little warmer, and the difference between the cold nights and the warm nights is incredible. The colder the camera is, the less noise it has. And quite frankly, it's kind of odd, but my mount seems to actually work better in colder weather too. So colder is really good for astrophotography. And if the seeing is good, this would be a great opportunity to get out and do some more. So it's not only seeing and not only transparency, but boy, the colder it is, that's really a great thing for astrophotography. Okay, with that, I will turn it over to David with Star Party News.
David,
all right. I just want to say, Doug, I love that narrowband, so I'm with you. I really like that one among the three. Okay, Star Party News for February. Got a little interesting as the meeting was actually even starting. Come on. Really, Mr. Computer? You're going to hang? There we go. Okay. Past Saturday, January 23rd, we had an event at the Hack Winery. We will talk about that. Coming up March 11 through 13, this weekend, next month, second weekend, is actually the club's trip to the Fort McCavett. I've got a few slides on that. We've got 5 more dates coming up with Hack that are under discussion. I was going to post them, but not with the first date. First date is kind of not acceptable, so this is always an ongoing discussion with them. Okay. March 11 through 13, Fort McCavett, 2021. This is the old, I believe this is the commander station with a partial moon. I forget who took this picture. I think it was Becky that might have done it. Exactly where is Fort McCavett? Well, over here you see on the far right-hand side, there's Houston, San Antonio. You come up to Kerrville. You come up to Junction, and by the way, the road between I-10 between Junction and Kerrville, as of right now, because of today's weather, is not passable. You come up here just past Junction, then hop up to where it says B, and you are at Fort McCavett. I believe it's 362 miles from my driveway. Your mileage may vary. And you come up, and you get to the fort right here. What I will be doing is I'm not going to give the whole thing. Is I've reworked this presentation and I will save it as a PDF and I will put it up on the website as early as tomorrow morning. Anyone considering or wanting to go, please get on the list and ask any questions. But you need to talk to Lisa Lester at lisa@riverofstars.net. She's the one who coordinates things with the fort, and she and Ken work out the space of who's staying where, and that depends on what you're bringing, whether you are wanting to stay in the barracks, staying in a tent, or bringing an RV, or if you're staying off-site, as some people have. All right. January 23rd, we had an event at Hack Winery, and you can see Trevor was there, and Chris, fresh from his stint at the store, brought this wonderful little equatorial daub that actually has the front rotating. It's actually a souvenir piece. It came from the stores. It was quite the highlight of the event, because you can tell it was somewhat cold in the pictures here of Chris and then Bob Eaton. But you see the shiny stuff out here in the center of the picture, just to the right of Bob? Yeah, that's called rain. It was unfortunately one of those events. Now, they did have some vendors. You can see here in the back behind Trevor. So there might have been about 75 people there, but there was not a lot of viewing. We brought the 6-inch daub. Wet areas back here. There's the cloud cover was low enough we couldn't even dial in on the radio antennas that are a few miles to the south. Trevor brought his rig. Rainy weather. I mean, it's always a pretty place to go to, but really wish we had something to show the people that night. And then this is Bob Eaton's reflector. And another vendor over here, and that was actually it. I had about 75 people there, and we pretty much packed up by about 8:30. Hopefully, weather will be better on forthcoming dates. So there is hope once we get past this wave and things are being good. People were social distancing. They were wearing masks. I think this will probably be the standard operating procedure for the short term. And with that, I thank you. And it's maybe aliens haven't visited our solar system yet because we only have one star. Maybe they're looking for systems with a 4 or 5 star rating. That's all, folks. Back to Doug.
Doug, you have a go.
Thank you. Okay, 4 or 5 star ratings. Very funny. Haha. Okay, David, thank you for those jokes you always put at the end of Star Party News. That's those are good. I don't know where you get those. All right, so that's it for this meeting. There will be no meeting in March because we're all going to go to Fort McCavitt, and so we hope to all see you there. As David mentioned, he's going to put up some information on the website about how you can attend Fort McCavitt. It's open to everybody that would like to come. It's March 11th through the 13th. It'd be great if you guys could participate in that. So our next meeting will actually be April 9th. And on that day, Dr. Brandon Riddell with UHCL and JSC will be bringing us radiation threats to spaceflight. So thank you very much for attending, and hope to see you at Fort McCavitt, and hope to see you at our meeting in April. Thank you very much for attending.